Hey guys, and welcome back again. And for this video I won't be using any notes to read off of, like paragraphs that I've written. So instead I'm just going to be using just like some information that I've accumulated together, and we'll see if it flows pretty well. Anyway, so in this video I want to be talking about change detection and error assessment. So before we get into that, we have to know about some pre-processing for multi-temporal analyses. So this can come in geometric, spatial, spectral, the four that I spoke about in my very first video. So geometric, spectral, radiometric, and temporal, and also spatial. Did I say that? I don't know. So in geometric, you really want the pixel sizes to be the same when you're doing time detection. Otherwise, the time detection will be influenced by different things in the pixel. So if you have a pixel size of one that's really, really small in your first image taken at like 2010, and one pixel size which is much larger in your image that's from 2020, then those two different pixel sizes will have different things within them. So a pixel of only 5 meters, that's really small, so 5 square meters, that can maybe only have a single tree in it. But a pixel that's like 20 square meters can have a tree and the car beside in it, affecting the pixel's value. So I've already been through lots of this stuff before. Anyway, in spatial registration between two images, remember we're talking about time detection. So anomalies between two different images taken at different times, that's what we're talking about. So I know I said before that the RMSE in the notes should be less than 1. I found a few sources which tell me it should be less than 0.5. But whichever you do should be okay. I'm just noting it here as less than half of a pixel size, so 0.5. And the images must have the same datum, projection, and same coordinates and all that. And they also have to have the same viewing angles. And then you have spectral issues. So in two different images, right, even if it's both, say, by like Landsat, the red band value can change. So the red band in Landsat 2010 image, that might be like 0.4433 or something. I don't know if that's red, I'm just making up a number. But the red band maybe in 2020, its red band value could be like 0.4438. So one which is 0.4433 and one which is 0.4438. So if a sensor, or if you're going to a different company for a different sensor, then how they define red can be different. So this will affect your spectral image processing, the effect of those two different images, looking at change detection. So if you're looking at change detection for like plants, healthy vegetation for near-infrared light may be defined differently than near-infrared light defined in another sensor, by another sensor. Then I also want to talk about radiometric, which is essentially just atmospheric conditions, but it can also be sensor quantization, which must be identical. So how sensors are calibrated must be identical, pretty much. And how you get estimates of particulate matter in the atmosphere should be exactly the same. So if you look at those two images there, just be in mind that in radiometric calculations between two different images at two different points in time, make sure that you have the sun at the same point in the sky, and it has to be the exact same season, and it has to be the exact same atmospheric constituents at either point in time. Yeah, and so that has to do with sensor viewing geometry and the solar geometry, so where the sun is, the time of day, and all that. And so that's temporal. And so if you want to see like a everything table of everything that you should be concerned with when you're comparing two different images at two different points in time, this table will show you everything that you pretty much need to know about. And so moving on to, that was the pre-processing for multi-temporal analyses. Now I'm going to be going into the actual change detection. like how you'll be doing this. So in change detection, you want to be, am I at the right place? I have no idea. So you want to first do the pre-processing, then you want to look at the number of data sets that you'll be working with. So data sets can either be bitemporal, which means 2 data sets, so two images or 2 maps, one 2010, one 2020, or it can be multi-temporal, which I mean you can like have images being taken every 6 days or every 10 minutes or whichever quality that you're doing. And then you'll be doing the change verification and error assessment, and then you'll be doing the presentation of change detection maps. So you'll be doing pre-processing, then you'll be looking at the number of data sets you'll be working with, then you'll be doing change verification and error assessment, so what change occurred and the error of that verification that you just did, and then you'll be presenting your information. And then we have image differencing. So in image differencing, looking at the difference between 2 images, you want to be basically just subtracting the earlier band data from the later band data. So the band 1 difference would be, so the digital number equals the DN of at date 2, so band 1 at date 2, so 2020 blue band, minus the blue band at date 1, which is 2010. So the later minus the earlier, plus some constant. And the constant is to remove negative values. That's all the constant is for. So if you have a negative DN, that's impossible. So the constant can be whatever it needs to be to make the DN positive, whatever you have to do in that case. And so areas of no change equals a value of 0, a DN of 0, and areas of high change should be plus or minus. Yeah, so like a minus would be, a minus would be a decrease, and a plus should be an increase, I would think. So you can see those 2 images right there. You can see that red circle, that's the area of difference that's been changed between the 2 images. So if you look at the left image, it's all white at the top right, and if you look at the second image, it's got some black there. And if you look at the difference image, which has got the red circle, that shows the white area where the difference has occurred. And you can also show this as another type of graph showing an increase in green or like a decrease in red, that type of thing. It's my next slide. Oh yeah. Change vector analysis. So change vector analysis or multi-date trend analysis. This is where we're detecting change and identifying the trajectory of pixel and magnitude of spectral change for each pixel. So all this is saying is that we're looking at the direction and magnitude. So you want to identify common change vectors to produce a classification of change. So like a typical change movement. So if you see vegetation in 2010 and you see it moving somewhere in 2020, you see you don't see the vegetation moving, but you see how much of it there is. You want to like make a best fit type line, saying where it is most likely that all vegetation will be in growth. So if you see that there is like say 10 units of vegetation, and then you see in the 2020 image that there's 30 units of vegetation, you could infer, depending on how much data that you have, that all vegetation will move by a factor of 3, from 10 to 30, so times 3. Then I want to move on to post-classification comparison. So this is where we have 2 images that are the same area that have been assigned to exactly the same classification. So if we have 2 dates, D1 and D2, so along the top you see date 1, underscore date 1, and along the column to the left you see underscore date 2. These are your 2 different points in time. Imagine that date 1 is 2010 and date 2 is 2020. And then you also have the same number of classes between both images. So this is in the scenario that I have in image 1, 2010, and image 2, where they both have the same number of classes, by which I mean like features. So what are the features? Well, you can have class 1, 2, and 3. So if you just look along the top, class 1, 2, 3, See, class 1 might be, say, vegetation, class 2 might be water, and class 3 might be artificial features. And so either of those classes can become something else in the new time period. So if you look at just the first column, class 1 underscore date 1, so if I had just vegetation, vegetation, if I move down, can become class 1, same thing, vegetation. So in 10 years from now in 2020, that vegetation could still be vegetation. Or it could be C2, class 2, which would be water, or it could become C3, artificial surfaces. That's what that's saying. So it's looking at the change of a feature over time, its chance of becoming a new feature is what it's trying to say. And so here's an example of what that would look like. So you kind of have like grassland in a closed open forest in 1988. So that's how much data might become the exact same thing, which is it appears in gray at the top left cell, or how much of it might have become grassland in 1997 in hectares. So that's just a very easy way of looking at it. And so now, before I move on, I just want to say one thing, is that you can do change detection statistics as a tool in ENVI. There's a tool called change detection statistics, where you can do all these types of processes. I'm just showing you like the background process to it. If you want to actually do it, we'll probably be doing it in the next video, I think. Oh, my voice is going. And so now I'm going to move on to time series analysis. So in time series analysis, this is multi-temporal change. And so you want to have low spatial resolution for more than 2 dates trend detection. So like that's what it is. So if you have a bunch of photos of the same area, so rather than taking one 2010, one 2020 image, you're taking, say, an image every 6 days. So you're going to have low spatial resolution for more dates. You're going to have a trend. You're going to have a bunch of pictures, and they're going to be low resolution, but you're going to have a picture so constantly that you'll have so many pictures of low resolution that you'll be able to see minor changes. So that's what time series analysis is all about. And also in this, you can break it down. A time series analysis is kind of like story writing, in the sense that you want to be able to tell what's happening over time. So you can you can see the seasonal number 1. You can see that red line seasonal. That's the second graph. So you can see it goes up and down every single year. This might be, say, like wheat, maybe. Maybe you're cutting wheat, and so you wait for wheat to hit its peak, and then you cut it and you farm it, and then you wait for it to hit its peak again, then you cut it and farm it, and it drops again and again and again. And so you want to see the trend. The trend is what's most important. Is the wheat output constant? No, it's not, because although it looks like each year we're producing the same amount of wheat, each time we're actually producing a little bit less wheat, because like the max peak later is less than the max peak earlier, and the max trough later is lower than the previous trough, the previous lowest amount and the previous highest amount. And you can make that into a remainder graph. And so what time series analysis really looks like is that if you go to www.intertidal.app, you can see this this page, this multi-temporal page. This is where you can select a year on the left and the right, and you can see the temporal change of, I don't know what this is for. This is tides. Right, so you can see like the effect of tides over year by year. And yeah, that's really what time series analysis is about. You can do this with like ocean currents or ocean temperatures, or you could even do it with vegetation or sand, like how healthy a beach is by how much sand it is. You can see the erosion of a beach is what I'm trying to say. And so here's another slide. You can see decrease, deteriorate. I'm not even going to try to say that. Deterioration, recovery, and increase. There we go. And so now I want to move on to, I think this is the second last bit. This is error and accuracy analysis. So once you've done all the previous parts, you then want to be looking at how accurate your data is. In error, there are a few types of error. There's 4. Let me just talk about the first 2 first. So there is the commission error, which is the number of pixels incorrectly included in an information class. And then there is the omission error, which is the number of pixels incorrectly excluded from an information class. So if you look at this blue area that I've highlighted, this is supposed to be class 1. This is what class 1 is supposed to have in that bell curve, but it doesn't. It's being taken in by class 2 because class 1 and class 2 are overlapping. So class 2 is gaining what it's not supposed to, and class 1 is losing what it's meant to have. So this is class 1's omission. Data is being omitted of what it's supposed to have. It's being kicked out. And class 2 is got commission. It's incorrectly including information that it should not be obtaining. Class 2 shouldn't have class 1's data, but it does. This is commission. So that's some very easy stuff. And then there is the second final 2 types of errors. These are the individual class error and the overall map error. So the individual class error, making sure that I got it right here. Individual class error is the error levels reported for an individual information class. So what does that mean? It might help if I first talk about the overall map error. Well, the overall map error is the average for the different class information. The different information classes, sorry. So if I have a bunch of information classes, say if I have a map and I have like trees and buildings, the individual class error is the error just for the trees layer, just the information class, just that one class, that one feature. Well, not that one feature, that one group of similar features, trees. And then you have your second similar feature, which is buildings. So those are 2 individual class errors. But if I get the averaged error for all of those, if I add them all up and get the averaged error, then that's the overall map error. So that's the individual class error and the overall map error. So the overall map error is just the individual class errors, all of them averaged together. That's what those are. Very, very simple. So then I want to be talking about, this is the final bit. This is the error assessment process. So the error assessment process is, you want to be looking at, well, the type of error. So you want to be looking at the sampling design. Do I have this not right? Oh, I think I omitted a slide accidentally. So the sampling design is you can have the simple random, systematic, stratified, systematic, or stratified random sampling methods. And you want to then select the reference dataset of high resolution base image, and then you want to compile the contingency error matrix, and then you want to evaluate the error matrix using appropriate statistics. So what does that mean? Well, in the first stage, which is each of your graphs, you want to have the then second stage, which is to select reference dataset, by which I mean the reference dataset can either be aerial photos, public knowledge, or field sampling, or it can also be the supervised classification method that I talked about in the previous video before the ENVI videos. The reference dataset is just like the layer that you're using as the base corrected image, the image that was already correct to begin with. The error assessment process is pretty much just assessing how correct it is or how incorrect it is. Then you have the design sampling scheme. Let's just skip that, that's nothing. And then you have compile contingency error matrix. So this is a pretty important part. You can do one of 2 things here. Close that actually. So in the compile contingency error matrix, you're showing the misclassifications and producers of an error total. So what am I trying to say? You're producing an error total. So you have an accuracy and an error. So the accuracy is the user's accuracy, which is the row total, and you have the producer's accuracy, which is the column total. It's not actually the total, it's just how much is affecting that total. And then you have the error, which can be the omission error, which is the column total. Then you have the commission error, which is the row total. So if I wanted to look at my omission error, how much data am I omitting that's supposed to be in that group? That's the column. So if I look at the residential group right here, my omission error is 3 of 73. So me being the producer, I have accidentally misrepresented 3 residential buildings as commercial. And on the commercial side, which is the second column, I have accidentally misrepresented 5 buildings as residential when they're meant to be commercial. So that's the omission error, which is again column totals. And then you have the commission total, which is again the rows. So commission is rows, omission is columns. And so the reference data is the columns and the image classes is the rows. There's 2 twos here. So the reference data should be right, and the image classes should be like as close as possible to that, pretty much. And if you don't want to do this compile contingency error matrix, you can do the root mean square error, which just explains the variation of points around the true value. And you can find lots of like YouTube videos and all that on this, Khan Academy or something like that. Yeah, that's just trying to find the final error. Anyway, I hope you guys have learned something. I'll be doing a video on this immediately after in like a couple days. And I'll be showing you this full process in ENVI, which is change detection and error assessment. Okay guys, so I hope you learned something.